So the title of my talk is Parallel MATLAB, the next generation, which alludes to the fact that we've had a product out called MATLAB MPI, which there are many of you who use in the lab today, and we're actually going to announce the sort of final version of that, which any of you can get from us. But we're really building another layer on top of that, which should bring Parallel MATLAB to all of you. That is, we think this is technology that is easy enough to use that any MATLAB user can make their program. If it can be parallelized, they can make it parallel with relatively little effort. I'd like to thank my collaborator on this, Nadia Trevenin, who had a lot, who basically wrote all the PMATLAB code, and likewise, if there are problems with it, talk to her. Yeah, sure. I should say the Parallel MATLAB is just sort of one leg of a whole vision that many folks in the lab have had about bringing advanced computing capabilities to the lab, nominally under the terminology of grid technology. This is sort of the software leg, which makes it so that you, the user, can make your programs parallel. There's a licensing leg. We worked very, very hard, and I think many of you in the lab are the benefit of a new licensing arrangement with the MathWorks that now allows us to run essentially MATLAB unlimited throughout the lab, and that was a huge step. And there's finally a hardware leg, which people are working on very, very hard so that we can provide hardware to you so that you can, you don't have to use your own cluster, or we will have a cluster available for you to do your computational jobs. Oh, next slide. So just a brief outline here, just a little bit on the motivation and some of the challenges to this problem. It's been a problem that's been worked on for a long time. There is a website maintained by a collaborator of ours, Professor Alan Edelman at MIT LCS, which is a taxonomy of all the parallel MATLABs out there. I think that's 31 and counting, and they even break it up into different regimes. Ours is fundamentally different from all of those in a very simple way, and I'll go into that later. Just talk a little bit about the approach, some of the performance results, and some of the future work. And I also threw in some slides here from a program called the DARPA High Productivity Computing Systems program, which I am the lead of one element of that on. Next slide, please. So just sort of the basic motivation, and this is for most of you don't think about the cost of code too much when you write your code, but a general rule of thumb in the Department of Defense is that 4 lines of DoD code cost the same as the workstation. So this says if there's a way that you can reduce the number of lines of code, that's a good thing in terms of cost. I think many people in the lab would agree to the fact that if we didn't have MATLAB, there would be many projects we couldn't even do because it would just take us too long to write the code. And MATLAB has been a fundamental enabler in the lab, and that's why we have over 1,000 users here at Lincoln. And so this is true across the DoD. There are many, and MATLAB represents one of a class of languages. There are many of these languages. MATLAB is essentially the winner of the war of these high-level languages in our space. The first technology we developed, which was called MATLAB MPI, which was a simple messaging library, essentially allows you the fundamental capability of parallelizing your programs, but with some work. Usually you had to write 50, 100 lines of code, and you had to know what you're doing, and Parallel MATLAB, which will be the next generation, will build on this. Next slide, please. So it's just why has this been hard in the past? This is something that we've found as we've looked at the user base out there. One of the biggest challenges almost of the other 31 approaches out there, they all use essentially a variation on the same theme, which is they have a function which they then call a C library with, and that C library is a parallel library of some kind. And that works fine, gives you a lot of capabilities. Unfortunately, you as a MATLAB user have no ability to extend or change that library. In addition, you have to sort of pull that enormous cost of that library into your environment. And that's essentially the reason why most of the other approaches have failed. One of the nice things about the MATLAB MPI approach is there is no other code except MATLAB code in the library. There was a central innovation there that allowed us to figure out how to write parallel programs and how to make programs communicate so that we did not need to interface with any other library. The result is a very, very small, very, very simple, elegant solution. It's a solution which is portable, so anywhere MATLAB runs, I mean, we do tests, we take it to another Unix system, it runs without modification invariably. It does have one performance penalty, which I will talk about, but for the most case, which is if you have programs where you're concerned about latencies in the milliseconds. However, we have found that most MATLAB users time their programs in minutes and hours, and so latencies in milliseconds are not such a big concern. However, for my group, which is the does high performance embedded computing, it's not necessarily. We've made a solution that's good for you. It's not necessarily good for all the problems we want to address. I just want to make sure that that's clear. So let me just talk about the approach, the MATLAB MPI approach, and then the new technology which really brings this to you in a much, much easier form. So the basic concept, one of the key things that we've learned in parallel computing, and I'll share this with you, it's something we really learned in the last decade, which is there were essentially two ways to bring parallel computing to the user. One was to take a messaging system, a messaging library, and to grow it up into a math library. That is, the messaging library MPI, which is the dominant one out there, has essentially tried to do this, and it's now 700 functions, and people find it's really hard to do math with a messaging library. Another approach has been to take a mathematical library and turn it into a messaging library. An approach that has been proven to be very, very difficult. Well, the thing that we've learned in the community is that these are two separate layers. You have a math library at the top and you have a message library down at the bottom. If you keep those two layers separate and have an architecture that integrates them in the right way, then you really get the best of both worlds. And the result is that our messaging library is very, very small, and likewise our math library is also very, very small, and they each do what they're good at. In addition, in order to make this run, the math library run in a different system, it requires only changes to the messaging library. For example, the moment we got our messaging library, MATLAB MPI, to run on a PC, this library ran on a PC without change, and that was sort of validation of that approach. So we have two products here, both of which are fine for you to use. One is this messaging library, which all it does is allow you to have two MATLAB sessions running, and they can send data back and forth to each other. Any variable in the MATLAB space can be sent back and forth to each other. This is all you need to make a parallel computing. This is all the technology you need. However, often if you're doing a complicated parallel program, the code for doing this is quite complicated and messy. So we've built a layer on top of that which allows you to do probably what it is that you want to do, which is create parallel distributed data structures. So these are, this would create a n by m matrix of ones. This creates an n by n matrix of zeros. And you notice we have this optional third argument here, which essentially tells that matrix how it should be broken up. So, for instance, if we wanted to break, this map could tell it to break this x up along the rows. So each set of rows was held on a different processor, and likewise y could be broken up on the columns. And through the power of operator overloading in MATLAB, this one line of code will just have done a parallel FFT and then what we call a corner turn or a full data transpose, and all the messages, which in this case would be a large number of messages that need to be sent to complete this operation, will have been created and executed for you completely transparently. And that's essentially the value of this library, is it takes all the bookkeeping, which is very mechanical and a lot of checking of conditions, and we've basically done it once the right way, so you don't need to do it again. And that's essentially the main story that I have here to present to you, and the rest of the talk will essentially be details on that story. So this is just a quick summary of some of the basic capability in MATLAB MPI. It's a very small number of functions. One of the things we learned in Group 102 through developing the various parallel libraries is that even though messaging libraries themselves provide an enormous number of functions, we only needed a very small number. And so knowing that, made me realize if I built just these functions, I could write any parallel program that you can imagine. And so that's all we've implemented in MATLAB MPI, and that's all we need. The central innovation of MATLAB MPI, and this is an idea that it could have been implemented 30 years ago, and I wish it had because it would have saved me a lot of problems, is that you can use the file system to send messages. And why is this important? Well, the dominant problem in a messaging system is what we call the buffer packing and unpacking problem, taking very complicated data structures, serializing them into a stream that can be sent over the network, and then unpacking them. MathWorks does this for you. There's about 100,000 lines, potentially 10% of all of MATLAB goes into writing out the data structures to a file. So by me leveraging what they have already done, i.e. using files to communicate between two MATLAB processes, I can leverage that 100,000 lines of code. I don't need to write it anymore. And that's essentially what we've done. And this system is very, very old technology. If you're the sender, this is the command you write. You do MPI send, an ID number, which is the destination, a tag, which is the message, a data structure, which holds all the information about the world, and the variable you want to send. And what MATLAB MPI does is it saves this variable to a file, okay, and then when it's done with saving it, it creates a lock file. The receiver, on the other side here, all they do is they do an MPI receive from a particular source looking for a particular tag, and this could be multiple variables. It doesn't have to be, you can send as many variables you want, and you can receive as many variables you want. You don't have to know what they are in advance. And this guy just sits and spins looking on the lock file. When the lock file exists, he knows that the buffer file has been created, and he loads it. It's very, very simple. This is ancient technology, and it was just something, I got this idea one night at a conference, and it's very simple, and it's worked out very, very well. And the result is a messaging library that's very, very small. Let's move on here. So this is a very simple MPI example. It basically sends a message between two programs. I won't go into the details, but the important thing is you see that although you can do this, okay, and I encourage many people are doing this all the time, and in many cases not a lot of effort, it still is not very pretty and requires, you know, when you get into complicated cases, it can be a great deal of bookkeeping to keep track of. So we knew that. The people in the parallel computing world know that the programming directly with messaging can be cumbersome. And so we wanted to develop what we call PMATLAB, or an ability, essentially this is our fundamental goal, to allow a MATLAB user to write parallel programs with the least possible modification to their existing MATLAB programs. And we had another other set of goals here that I won't go through, but this was essentially a contract and an agreement that myself and several other folks at UC Santa Barbara and at MIT campus, we all collaborated and said we want to create a unified interface, which is sort of the way that people should write parallel programs. And we will have multiple implementations of that interface, but a user can just write one parallel MATLAB program, and there'll be many ways to support it. And so this was our foremost goal here, and we think we've achieved that goal. So we'll get into that in the next slides here. So this is basically a structure of a parallel MATLAB program. There's some initialization and some finalization, of course, that you have to do whenever you bring in a new library. What I'm going to do here, this is essentially the example I talked through before. You create a map, and this map is storing three pieces of information. First is how I want to break up a data object. I'm going to be dealing with a matrix, so two dimensions. Should say capital N here is the number of processors I'm running on. Little n is the size of the matrix. And so I'm telling this I want to break this matrix up along the columns, and I want that matrix to live on just the first half of the processors. And then for map Y here, I'm telling it I'm going to break it up along the rows, and I want that to be on the second set of processors. I then go and create these two matrices, very much similar to the way you would write your normal MATLAB. And then we've overloaded FFT and the equal sign, and so you just do this operation now. And this is, like I said, essentially a full pipelined FFT with a transpose communication between two stages. The amount of lines of MATLAB code, MPI code you would need to write this would probably be several thousand, and we've compressed it to essentially one line here. And that's just one example. Just talking about some of the basic functionality that we have here. The data structures we support today are up to 4 dimensions. We can add more if people decide that that's really critical. We found 4 to be enough. If you want more, Nadia will just have to lock herself in her office for a while. And we usually, with this type of, it's a lot of mathematical bookkeeping. It requires a young mind to work on it. And so Nadia is, you know, still young enough that she probably can work on it, but she may not want to anymore after doing this once. It supports, we're taking a page out of the MathWorks playbook. That is, whenever MathWorks introduces a new data structure, for instance, they introduced multidimensional arrays a few years ago, or they've just introduced ints and cars and other types of data types. The way they introduce that to the community is as a storage class first. You can put data in it, you can get data out of it, but you can't really do operations on it. And that's essentially how we're starting out here. These are parallel data structures. You can put data in them. There's some operations that will work on them, but for the most part, if you actually want to do a computation, the easiest thing to do is to get the data out of it, which can be done with a very simple command, and do your operations and stuff it back into it. It supports a variety of distributions, and I feel free to talk to me about if you want to know what the definitions are. Basically, you can break up your data in uniform blocks. You can break up your data in cyclic distributions, so you can distribute the data sort of round-robin style. We have block cyclic distributions, and we also support overlap. This is if you say you're doing image processing and you want to do a filter and you need edge conditions in order to do that parallel computation. We have a nice mechanism for allowing you to do that. And then we're moving forward here. Through code generation, we could potentially overload the entire library if the user base demanded that. This is, in a certain sense, the announcement of this product's initial availability to the Lincoln community. So we want people to come and ask us and try it out, and then let us know what pieces they need, and that will steer us in terms of what parts we build. There's a lot of things we can envision building, but we'd really like to have the user base begin to drive us on that. So I'm just going to talk about some performance results from MATLAB MPI and then Parallel MATLAB. So this was this observation I made before. So this is a classic bandwidth curve. It's sort of bandwidth as a function of the size of the message you're sending. And what we noticed is that we have 2 approaches here. One is using MATLAB MPI, and the other is using the native C library. MATLAB MPI, as I said before, uses files. The native C library uses just the network. The important thing to notice here is for large messages, the bottleneck for them is the same. That is, writing to disk is very, very fast. That's not the bandwidth that's not the bottleneck in this situation. So for large messages, you get the same performance. The basic difference is the latency. File latencies are in the millisecond, network latencies are in the microseconds. So if you have a hard real-time problem, like in the seeker of a missile, this isn't the right technology for you. However, like most users around the lab, when you're processing terabytes of collected data, you're not really worried about milliseconds. You're usually worried about hours or days of time, and that's what we can really provide for you here. This technology scales well. It's here we did a timing on 2 processors versus 16 processors. So we've come up with technologies that allow all the processors to talk to each other in a very scalable way. There's no inherent bottlenecks in the system. Perhaps the biggest development now is that MATLAB MPI runs on Windows XP. I haven't tried it on other systems. I don't even have a Windows system on my desk, but I did do this, and we think there will be a lot of users who want to try this out. And that stuff's not as new, but that stuff is not as mature, but we, again, encourage Windows users to try things out and let us know, how they like it, how they don't like it. We have had people use this actively, and they like it. So the next, can you go back to slide? So this is just some more scaling performance. We look at a classic thing we do in parallel processing is we look at the speed up of a program as a function of the number of processors, and the goal is to be linear. This was a fixed problem that was a very large problem that we then chopped up into small problems. And we got what is sort of classical superlinear performance here. MATLAB is a memory hog. It uses a lot of memory. So if you can come up with a way of chopping it up so it's several small memory problems instead of one large memory problem, your performance can actually go up in a superlinear fashion. We've also run it on very large, this is a scaled problem. Basically, we grew the problem as we added processors. So we've run it on as many as 300 processors. We mainly did this so that we could test the infrastructure. There was a lot of changes that we made to the library once we tried to get it to run on 300 processors. But we've made those changes and we have a nice system now that should scale up to a very large number of processors. I haven't tried it on 3,000 processors. At some point we'll try it, and I'm sure we'll have to make some more changes when we go to that scale. Just as one example, and that's an IBM to PC thing. There's supposed to be a picture there, but this was some work we did with folks on campus on various cognitive algorithms, basically a contextual vision application, a text processing application, an image segmentation application. They were parallel in different ways. The main thing to notice here was, well, I actually parallelized these codes myself. I know nothing about these particular areas, but I'm pretty good at parallelizing algorithms. And so this is the number of processors we ran the algorithm on. This is the speed up that we achieved. This is the time it took me to get that level of speed up from the time I first got the program. And so this is 3 hours, 8 hours, 4 hours. This represents approximately 2 orders of magnitude reduction in time versus the traditional approach of taking MATLAB, converting it to C or C++, and then making it parallel that way, which is sort of the standard approach that we've done in the past. So this is a huge step forward, and we have many, many users out there using MATLAB MPI and getting this kind of performance. This just talks about some of the different applications. I stopped tracking it now. It's been on the web for almost a year. I need to update this, but we're probably at about 1,000 users of MATLAB MPI in the community. It's probably the most widely used of all the parallel MATLAB technologies. There's been classes taught with it. Professors have liked it. Basically, the main reason they say of all the ones I've tried, it was the one I was actually able to get to work. And that's essentially, it's not a high bar that you have to achieve here. That is, just getting something to work is a significant success. I should say it's not perfect. We have the highest success rate with our users, out over the web when I've done. I'd say about 70–80% of them are able to get the thing working, but still mean that 20 or 30% for whatever reason got down some dark alley and never were able to come out. And usually when that happens, they abandon the product. And we try and get information about those. And usually it's they something about their system wasn't quite configured correctly. So it's a big improvement, but you can still sometimes you need a little help. And fortunately, you have people around to help you with it. So I'm just going to talk about pMATLAB's performance results here. The first thing we did, and this is always step one when you're building a library on top of a messaging library, is you measure the overhead. That is, okay, this blue line. I'm sorry, this black line is the messaging performance of MATLAB MPI. pMATLAB will never exceed that because it's built formally on top of MATLAB MPI. But we wanted to make sure we weren't degrading that performance by too much. And Nadia did a lot of really good work to make sure that this was the case. And we have a very nice curve here there is a slight degradation in performance, but it doesn't grow with the size of the messages or anything like that. And it's essentially we've doubled the latency in this particular system from 35 milliseconds to 70 milliseconds. We think that's well worthwhile for the types of productivity enhancements that you'll get. In addition, I must say that for most MATLAB MPI users, I thought initially there were going to be a lot of them sending messages in this regime. Turns out they're sending messages over here. Most MATLAB MPI users, they start a program and they broadcast an enormous amount of data to all their worker processors, maybe half a gigabyte of data. So this is not the low latency that, they're usually taking 5, 6, 7 seconds to transmit the data. So this has usually not been a problem. I was surprised that that's how most people used it, but that's actually what they're doing. This is a little clutter simulation program that was put together with the aid of Nick Pulsone. It's supposed to look familiar to people who do clutter simulations. It doesn't look particularly familiar to me because I don't do clutter simulations. But we basically create a complex matrix, distributed matrix of rands here, and then another of zeros. We create some coefficients and weights, and then we essentially convolve them. We've overloaded convolve so that this works, and then we do the weight multiplication, and again, we get nice performance here. And you see this code is very, very similar to what you have written. The only changes you need to make are adding these maps and putting these maps in here when you created the data structures, and the rest of the program essentially looks the same as what you had before. This is a much more complicated program. This really shows off the capability that we've brought together. So one of the dreams I've always had, and I've often been involved in situations where there's a guy who writes a simulator for a sensor system, because we always want to test on simulated data, and then he generates these gigantic data cubes, which a person who's doing the signal processing then runs on, and and to me, the sort of it should be a closed loop there. Wouldn't it be great if you had a real-time simulator that immediately fed right into your real-time processor, so you could make the simulation and processing loop much slower. Much faster. You can always make things slower. We've done that in the past too. So so we have a parallel data generator and a parallel signal processor here. It's 7 stages, and I've mapped different stages to different numbers of processors, which is shown by the color here. And between different stages, we have these corner turns or transpose operations necessary so that you can work on different slices of the data. And this is a very, very complicated thing to do. To implement this in MATLAB MPI or in any messaging system would require an enormous amount of code, and you would probably not get to the end of it. You would probably go crazy before you actually got all the bookkeeping correct. And this shows the actual code here that we wrote. So this is, and what I have here lined in blue here is the implicitly parallel part of the code and the required changes. So this is basically a serial MATLAB program here, and all you had to do is add the maps, and then all these different, all that full pipeline gets set up inside here, essentially automatically. And again, this would have taken an enormous amount of code, but you can do it relatively easily. So let me just finish up here, get to some of the future work and the summary. And I should say that we do have even more tutorial level material that really gets into sort of how do you actually make this work for you. I'd be happy to share that with you as we unroll our capability out to the entire lab. We want to create more materials like that because there are some concepts that you have to be. And I've worked with people, and usually they can be drawn out on the whiteboard in about 10 minutes about what does it mean to break up a data structure and how do I actually use that to do my parallel computations. So one of the things that we did this past year is, so we've been involved in a couple of exercises with groups that basically there was an analyst who needed to go out in the field, they were collecting data, and it would have been great if they just had some way to process the data. It didn't have to be real time, but fast enough that they could have influenced the mission. They could get, if they could get an answer in 5 minutes, 10 minutes, or whatever, before the phenomenology is changing, then they could really influence the mission. And so in the past, what we did is we converted it to C++, and but it wasn't the algorithms weren't really fixed, and the analysts wanted to play around with things, and so it had some challenges it left you sort of wanting. And so one of the things we've noticed is that you can now buy pretty dense, very inexpensive bladed clusters. So this is a 28 processor cluster. It's about that big. It's about $50,000, $60,000, so it's not that expensive. It's very heavy. It's about 400 pounds, but you physically can take it. It's much more transportable than a full rack. And so what we want to do is basically we're going to do this for a limit. We're going to put this on board the 707. It's going to connect up to the RAID disk recorder, this fundamentally enabling technology, because the only interface between these two is a file system. It doesn't have to interface with the whole sensor. It just sees files. And then we run parallel MATLAB on this whole thing, and we get to use the actual it's the same analyst code that they're using now to look at the algorithms. We parallelize that, and then we can run that in the air. And then we believe this will take data processing that would take 5 hours and bring it down to about 5 to 10 minutes. So that's a big difference, and that can make a big difference in a mission. Essentially answer the questions: is the lens cap on, or whatever. I mean, you can actually, rather than having to potentially check all the data if it didn't work out, or having to wait till you process it on the ground. So I'm very excited about this. And Lou Tella is the guy writing the code for this project, and he gave me the code, and we were asking, well, when are we going to parallelize this? How are we going to get this parallelized? And I was like, this stuff's supposed to be just easy. One night during a commercial break, I'll parallelize it. And literally, if you know what you're doing, this can be done in a couple minutes. So we've sort of taken another 2 orders of magnitude off the time it takes to parallelize this stuff. So, I mean, it literally is changing a few lines of code. But you have to know what you're doing. You have to still know how this is going to go onto a parallel computer. And that's where you might need still to talk to us a little bit to get a basic introduction to parallel computing. But the actual number of code changes you need to make is very, very small. This is some of the performance we achieved on an initial test. Let me move on here. So we are advancing this forward. One of the things, and I've sort of alluded to before, one thing we want to do is really demonstrate this in a large multi-stage application. We're looking at a variety, SBR, other types of applications, and really show that we can do, a really large application with this. We're very confident that we can do that. Another thing we want to do is incorporate some kind of expert knowledge into the system, so that right now you still have to know the best way to break up your algorithm in order to get parallel performance, okay? And that can require some knowledge about parallel algorithms and about parallel computers. We're hoping to add some smarts to this technology so it can help you, and you don't have to know as much, or it can find solutions or search for solutions that you might not be able to find. And then finally, one of the things we would like to do is explore a way to actually get this onto embedded systems. There are many systems for which, MATLAB code would be fine if it just could be made 5 or 10 times faster, and you could get it onto an embedded platform. There'd be a lot of applications that wouldn't be sufficient, but again, there's many cases where that's good enough, and the sponsor would be happy with that. Then finally, I want to talk to you a little bit about another program that I'm very heavily involved with, which is called the DARPA High Productivity Computing System Program. This is a program to build the next generation of economically viable computing systems, as well as develop, and this is where I come in, a new procurement methodology for buying these systems. So this is a program that had about $20 million phase 1 activity involving 5 supercomputing vendors. There was an initial team led by MITRE. Lincoln is sort of taking the handoff from that team. The MITRE folks are still involved. And I'd say there's about 15 institutions and about 30 people involved in the team that I'm leading for this activity. Cray, IBM, and Sun are going to get about $50 million each to build this or prototype this next generation supercomputer. And the Lincoln team is going to be in charge of coming up a way of fundamentally changing the way we value these systems, so that we really, right now the problem is they have these 10,000 processor systems and no one can program them, and the cost of programming them is really, really high. And so we want to create a way of valuing these systems so that if you produce a computer that costs a little bit more money but it's a lot easier to program, we have a way to buy it, because we don't really have a way to buy that system in the future. This is just a little bit more about who's involved. These are the industry partners. We have a variety of mission partners: Department of Energy, NSA, a bunch of 3-letter agencies. This is the productivity team that I lead. A really great cast of folks from all over the country who have unique expertise. And just a teaser of one of the things we're looking at. This is sort of my graduate career on a single view graph, which is I, over and over and over again, tried to make a particular application faster. It was just an image filtering application. And I've programmed it up in all these different ways. And one of the things I was able then, in retrospect, look at was what's the performance I achieved and what was the effort. And so what we want to do is come up with generic curves for the community about this trade-off between how much performance I get at what effort, so that maybe I can't get the best possible performance, but if I can do it for a lot less effort, that's a big win for the community. And we right now have no way of doing that trade-off. And so part of the goal of our team is to be able to do that for this community. So just to summarize, so I said, MATLAB MPI, it's a product. You can get it from us. We'll be putting it on the Lincoln website if you want to get it from there. It has the basic functions necessary for doing parallel programming. The performance can match a native messaging system, so it has good performance. We've demonstrated scaling into hundreds of processors. And pMATLAB allows users to, that's our sort of layer on top of this, allows you to really sort of you can still think the way you want to think in MATLAB. You can think about matrices and arrays, which is the way you think. You don't have to think about passing messages around. And you can write very complex codes. And we really want you to come and, send email to me, send email to Nadia, and we'll try and hook you up with the technology and really get this out there. And our belief with the pMATLAB technology is, unlike MATLAB MPI, where maybe we were still a little bit involved, this is really, you take it, and it should be simple enough that you can just do it yourself. You don't really need, much involvement for us. And we think the amount of changes you have to make your code is sufficiently small, and that we've provided a good number of examples for people that they'll be able to do this. And finally, I want to just mention again, we're collaborating with the campus, Ohio State, and UCSB to define this sort of unified parallel MATLAB interface. They have their own technology. It's called MATLAB Star P, which is sort of along the lines of connecting to an existing parallel library. And our goal is to have one interface. So whether it's the Lincoln pMATLAB that's the engine underneath, or the MATLAB Star P underneath, you could do whatever one you want, and you could write one parallel program that would work in both environments. So that's just the end of the talk, and I'll take any questions.